Hello and welcome to the Quality Excellence channel. I'm Mayank Agarwal, and in today's Lean Six Sigma training, we'll explore Chapter 18, Normal Probability Distributions. Today, let's unlock the secret behind smart, data-driven decisions. We'll delve into the power of understanding data distributions and how they can transform the way you approach problem-solving in Six Sigma. Forget guesswork. We're entering the realm of informed action, where every decision is backed by solid evidence and statistical insight. At the heart of it all lies the normal probability distribution, or as it's more commonly known, the bell curve. This elegant curve is more than just a shape. It's a powerful representation of how data tends to cluster around an average value. It's a visual story of the underlying patterns in your data. Imagine tracking pizza delivery times. Think about all the factors that could influence how quickly that pizza arrives at your doorstep. Traffic, the skill of the driver, the efficiency of the kitchen, and even the weather. When you collect enough data, you'll find that most deliveries are around the average time. A few are exceptionally fast because the stars aligned, and some are unfortunately slow due to unforeseen circumstances. That's a probability distribution in action. It's a way of organizing and visualizing the range of possible outcomes for a particular process, showing you how likely each outcome is to occur. Think of it as a map showing how often each outcome happens. It's not just about knowing the average, it's about understanding the entire spectrum of possibilities and their relative frequencies. In Six Sigma, distributions help us visualize and understand our process data. They provide a framework for analyzing the performance of our processes and identifying areas for improvement. By examining the shape and characteristics of a distribution, we can start revealing patterns, assess consistency, and quantify variation. This is crucial for making informed decisions about process control and optimization. The bell curve is special. It holds a unique place in the world of statistics and Six Sigma. This is because so many real-world processes, from manufacturing to service delivery, tend to exhibit this pattern. It's a fundamental characteristic of many natural and man-made systems. Consider things like test scores in a classroom, the weights of products coming off an assembly line, or even the heights of people in a population. Time and again, you'll find that these types of data naturally follow this shape, clustering around a central average with decreasing frequency as you move further away from that average. When our data is normal, meaning it closely resembles the bell curve, we unlock a treasure trove of analytical possibilities. We can use powerful statistical tools to predict performance, identify potential problems before they escalate, and make data-driven decisions with confidence. The bell curve provides a solid foundation for statistical inference and process control. For example, if we plot the thickness of thousands of smartphone screens as they come off the production line, we can gain valuable insights into the consistency and precision of our manufacturing process. If we observe a tight, narrow bell curve, it means our process is highly consistent. The screens are being manufactured with minimal variation in thickness. This is a sign of a well-controlled and reliable process. However, a wide, flattened curve signals too much variation in the screen thickness. This indicates that there are factors influencing the process that need to be investigated and addressed to improve consistency. In essence, the bell curve is our guide to measuring and improving consistency in any process. It provides a visual representation of process performance, allowing us to identify areas for improvement and drive meaningful change. It's a cornerstone of Six Sigma methodology, empowering us to make data-driven decisions and achieve operational excellence. What makes a normal distribution normal? It's a question that statisticians, data scientists, and even everyday observers have pondered. The answer lies in a few key characteristics that define its shape and behavior. We're about to dive into the fascinating world of the bell curve and uncover the secrets behind its ubiquitous presence in data analysis. Symmetry. This is perhaps the most visually striking feature of a normal distribution. Imagine drawing a line straight down the middle of the curve. The left and right sides mirror each other, perfectly balanced. This symmetry indicates that data points are equally distributed around the central value. It's a visual representation of equilibrium, where deviations above the average are just as common as deviations below it. This balance is a fundamental aspect of what makes the normal distribution so predictable and useful. With the mean, which represents the average value of the dataset, median, the middle value when the data is ordered, and mode, the most frequently occurring value, all converge at the center. This alignment is a hallmark of the normal distribution, signifying a strong central tendency. When these three measures coincide, it reinforces the idea that the data clusters tightly around the average, making it a reliable indicator of the typical value. The empirical rule is key. It provides a framework for understanding the spread of data within a normal distribution. About 68% of data, a significant portion, falls within one standard deviation of the mean, meaning that most of the data points are relatively close to the average. This concentration around the mean is a defining characteristic of the normal distribution. 95% within 2 standard deviations of the mean, capturing the vast majority of the data, and 99.7% within 3. This means that almost all data points lie within 3 standard deviations of the mean, leaving only a tiny fraction as outliers. This predictable spread is what makes the normal distribution so valuable for making inferences and predictions. For example, if average call time is 5 minutes in a call center environment with a 1-minute standard deviation, indicating the typical variation in call lengths, most calls last 4 to 6 minutes. This understanding allows managers to effectively schedule staff and anticipate workload. This predictability lets us set expectations for performance and resource allocation and spot outliers, identifying unusual events or data points that deviate significantly from the norm. These outliers might indicate errors, anomalies, or opportunities for further investigation. In a chip factory, where consistency is paramount, if most bags weigh close to the target weight, ensuring customer satisfaction and regulatory compliance, and nearly all fall within a narrow range, adhering to strict quality standards, the process is in control. This indicates that the manufacturing process is stable and reliable, producing consistent results. The bell curve's consistency helps us ensure quality across various processes and minimize defects, reducing waste and improving efficiency. That's why Six Sigma practitioners love the normal distribution. It's a cornerstone of their methodology. It makes process performance transparent and measurable and manageable, allowing for data-driven decision-making and continuous improvement. Use the bell curve to predict future outcomes, control your processes with precision, and improve your results, driving efficiency, reducing costs, and enhancing overall performance. The normal distribution is more than just a statistical concept. It's a powerful tool for understanding and optimizing the world around us. How do we know for sure if our data is normal? Well, we check. Start with a histogram. It's a great visual tool. If it looks like a bell, that's a good sign indicating a normal distribution. Box plots help too. They offer another perspective. A symmetrical box and whiskers suggest normality in your dataset. For more precision and accuracy, use a normal probability plot. If the points form a straight line, your data is likely normal and well-behaved. For a definitive answer, run a statistical test like Shapiro-Wilk or even Anderson-Darling. If the p-value is above 0.05, your data passes the normality test. If not, it's time to dig deeper and investigate further. Always check your data's shape before choosing your analysis tools. Confirming normality is the first step to reliable Six Sigma analysis. What if your data isn't normal? What if the bell curve you expected looks more like a lopsided mountain range or a flat plateau? It's a common challenge in data analysis, and it can feel like you've stumbled into uncharted territory. You might start questioning your methods, your data collection, or even your entire project. Don't panic. Real-world data often isn't. In fact, perfectly normal distributions are more of a theoretical ideal than a practical reality. Embrace the messiness, because that's where the interesting stories often lie. The key is to understand why your data deviates from the norm and to choose the right tools to analyze it effectively. First, investigate. Are there outliers, errors, those rogue data points that skew the entire picture? Are there data entry mistakes, measurement inaccuracies, or other glitches in your data collection process? Identifying and addressing these issues is crucial before you proceed with any further analysis. Or mixed processes. Is your data coming from different sources, different populations, or different operational procedures? Combining data from disparate processes can often lead to non-normal distributions. Consider segmenting your data to analyze each process separately. Clean up the data if needed. Correct errors, remove outliers if they are truly invalid, and ensure consistency across your dataset. Data cleaning is a fundamental step in any analysis, and it's especially important when dealing with non-normal data. If non-normality is genuine, try a transformation, a mathematical function that reshapes your data to better fit a normal distribution. This can make your data more amenable to traditional statistical techniques. Logarithmic or square root for right-skewed data, where the tail extends towards higher values. These transformations can compress the larger values and spread out the smaller ones, bringing the distribution closer to normal, or boxcocks for more complex cases. This is a family of transformations that can automatically find the optimal transformation for your data. These tricks can turn a skewed distribution into a bell curve, making it easier to apply statistical methods that assume normality. Unlocking powerful statistical tools. Techniques like t-tests, ANOVA, and regression analysis often rely on the assumption of normality. Remember to interpret results back on the original scale. After transforming your data, any conclusions you draw need to be translated back into the original units of a measurement to be meaningful. For example, if call durations are skewed, with many short calls and a few very long ones, a log transformation can reveal a normal pattern, allowing you to use standard statistical tests to compare call durations across different agents or time periods, making analysis valid. Without the transformation, your results might be misleading or inaccurate. The right transformation lets you measure and improve even messy processes. It provides a clearer picture of the underlying patterns and relationships in your data. Adapt your approach to fit your data, and don't be afraid to explore different transformations or alternative statistical methods that don't rely on the assumption of normality, and you'll always find actionable insights. By understanding the nature of your data and applying the appropriate techniques, you can unlock valuable knowledge and drive meaningful improvements in your business. Why does all of this really matter in the grand scheme? Because Six Sigma tools like t-tests and process capability analysis assume normal data. Using the wrong tool on non-normal data leads to bad decisions. If your data is normal, use parametric tests. If not, transform it or use non-parametric alternatives. Understanding your data's distribution is the foundation of effective analysis. The bell curve helps us set limits, predict defects, and measure improvements effectively. Mastering distributions turns raw data into real business results. Embrace the bell curve. It's your key to unlocking Six Sigma success.